So what they did on this counter is they're calling this clock A, and then down here they're calling this clock B. So on our original thing, what we did is we took this one and fed it into this one, right? You understand? And we took this one. I don't leave myself enough room. So originally when we drew this out, we took the Q output of this one and we fed it into this one. We took the Q output of this one and we fed it into this one. And we took the Q output of this one and we fed it into the clock input of that one. And here was my original clock right here. So this would be what they're calling clock A. Now what they did on the 7493 and the 7490 and the 7492 is they did not connect this clock right here. So what we're going to have to do external is we're going to have to put a jumper between this clock input and then the clock B. Oops, wrong place, Rich. Between the clock B input. Now why they did that is because if we don't use a modulus, if we want to set this thing as a frequency divider, and we need a 50% duty cycle. If you don't use a divide by 2, a divide by 4, a divide by 8, divide by 16, then your last output is not going to be a 50% duty cycle. So the way they set this up is I can divide this out and I take the output and feed it into this guy, and we would always get a 50% duty cycle. So that you would feed it backwards if you needed a 50% duty cycle, which is okay. But what we're going to look at now is that's why they separated. That's why we have two clock inputs. So what we have to do when we set this thing up is we have to connect the QA output. We have to connect the QA output back to the clock B input. On the 7490, the 7492, and the 7493, we have to do that. That's not done internal. So when I wired this thing up, and I've got it wired up for the lab, and we can do about what we want to with it. So what I had to do is I had to take the what? The QD output and bring it back into the clock B input. So this is the one we're dealing with right here. What does NC mean? Not connected, because all these have basically the same pin out. It's just that over here we have a reset 0, reset 9. Here, since this is a divide by 12, we don't have a reset 9, but we still have the reset 0 on the same pins, right? You understand? Down here we don't have a what? Pin 4 is not connected on any of them. But we don't have a reset 9, but we need a reset 0, right? Y'all understand? So all these are not connected on the 7493. 7493 is a binary counter. It's a 4-bit binary counter, so that means if we leave it alone, it's going to count from 0 to 16. 0 to 15. So this is the guy we got, right? This is the pin out. And then we'll hook up a circuit in the lab. See what we need to do there. So the way I have it, and I'll show you all the circuit. I have these two guys connected to switches, so I can determine when it. Oh, by the way, I need to do that too. Let's see if this is. Okay, I'm going to switch over to the camera. This is not really the lab. I'm just going to show you how this wired up. Okay. And what I'm doing is I'm going to take this thing right here. This is my count in. And I'm going to, first of all, it's starting off with 7. So when you turn these things on, they're going to come up random, right? You understand? So what I'm going to do is turn it off and turn it back on. It did come up 0. That was very unusual. It's coming up 0 every time. But what if it came up with a number? So here, okay, so here here we go. So I've hooked up the QA output to light 0. I hooked the QB to light 1, QC to light 2, and then the QD to light 3. So right now I got a count of 0. Okay. Count of what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or A, B, C, D, E, F. What's going to happen with more count? It's going to roll back around to 0. You can't say it resets. It rolls back around to 0. This is at 93. This is the binary count. Because if it was the 7490, it would have rolled around on 9. If it was the 7492, it would have rolled around on 12. Now, if I need to count further, guys, what I would do to count further is I would come over here. So here's 174.93, and we'll put it this way. And this is QA, this is QB, this is QC, this is QD. Then I would have another 74.93 or 74.93. Now what I've got is I've got the Q. I'm bringing my clock in on clock A. And I'm taking this guy right here and I'm bringing it into clock B. So what I have to do the same thing over here. This is clock A. What I would do is I would take the D output of this one and I would feed it into clock A. And then I would take this one. On these guys, I'm going to have to take these. I'm going to loop it around so it makes sense. And I would hook this into clock B. So now I can count from 2, 4. This would be 2, 4, 8, 16, 32, 64, 128, 256. So I could count all the way up to 255. But your propagation delay would be set by this guy. So this would decrease the speed of your count a lot with these ripple counters, right? You understand? And if I needed to count further, I could do what? Add another one, take the D output of this one, feed it into that one, and I'm not going to draw all the rest of them, right? You understand? So now we can count up to 512. I'm sorry, for 511. We can count up to 511. So I can keep adding these things and we can get just about any count we want to, right? You understand? But now the propagation delay would be set by this guy. So that means our count, the speed that we could count at would be a lot slower. So this is kind of strange that I have to do this, but like I said, they set it up so we could set the modulus of the counter and feed it into the A count and get a 50% duty cycle out if we needed it. What I'm going to do is I'm going to take my clock output off of this. I'm going to take my count output off of this guy, and I'm going to move it over to one of these switches. Well, what's going on? I ain't counting that. What'd you say? The bounce, yeah. So when you bring a counter into these counters, these guys are fast, and it will count the bounces, right? You understand? So mechanical switches bounce. So if I've got something out there counting cans that's flying by, and I have a mechanical switch that hits that, we're gonna have to debounce the circuit, right? You understand? And so that's the difference between these guys and these. These have that tieback NAND gate inside there, and I showed you that where it debounces. Okay, so I want to reset it. I'm going to come over here, bring reset 1, nothing happens. So to reset this thing, we have to bring both of them high, right? To reset, yeah. Oh, I needed to get my labels off here. That's no longer true. Oh, we're okay. Set count. We're not on any figure. We're going to come back up here. What I've done is I've wired all the inputs. So the way I have this wired now is I have this guy hooked up to pulse. And then my 2 resets, they're both high active. I have a reset 0 and a reset 1. I think your data sheet, the one in the lab book is, in the lab's not the way the data sheet. I'll explain that when we get over there, right? So they call it CP0 or CPA and CP. It's not actually, it's actually clock A. So clock A is going to be CP0 and clock B is going to be CP1, right? You understand that? So what I have is I have these two. So I have this one connected to switch 0, and I have this guy selected to switch 1. Now these are my reset 0, reset 1. Huh? Yeah, that's memory reset. And why they call that, I don't know. I don't know where data sheets they got these things from, but if we look at any data sheet on the 7490 or 7493, it's going to be labeled just like the data sheet we looked at. And then the outputs, what are they calling the outputs? So they're doing that right? And then a VCC and common. Wait a minute, I'm redoing these. So I have my clock connected up to the pulse. Y'all understand, we're not connected to a switch. We're connected to a circuit that's connected to the switch, right? Even for the clock. So I'm not connected it to the pulse switch. I'm connected it to the debounce circuit for the pulse output. So these are outputs. Just like the switches, we're not connected to the switches. We're connected to a circuit that sets up a legal logic, right? That way. And then what I have on my reset 0 It's called RS though on the data sheet, right? No, on the actual data sheet. Yeah, those guys are wrong, right? RO, yeah, reset Z. It's actually R0 for reset 0, but it's reset 0. It's reset. So it's R0, reset 0, 1, and reset 0, 2. So it erased all that. Maybe it didn't. Let's see. There it did. So I have clock A connected to what? The pulse output. Then I have R01, R02. I have this connected to the circuit controlled by switch 0. And I have this connected to switch 1. This is QA, QB, QC, QD. So I have QA connected back into clock B. So this thing will count, right? So this is the circuit I have. And then of course I got power, which is VCC is on 1, 5, and then common is on pin 10. So this is moved again, right? So that's what I was saying. When you get into your combinational logic circuits, make sure you look at the pin out on where these powers are connected. All your basic gates, they're always on the upper right hand side and the lower left hand side, right? You understand? But on these combinational gates, they're basically sometimes in the center, right? You understand that? So this is the basic circuit for this guy. So there it is right there. So we need to do our pin out right on the lab. So here's my power connected up to pin 5. Here's my common connected up to pin. What is it? Right here, it's hard to see. Then this is my outputs going up to the LEDs. I think they're split by that, right? They're split by the ground, the common pin. And then my clock output, I got it hooked up to the debounce. So it didn't take long to wire up, but if you was to have to wire this up transistor wise, you'd be talking about 100 wires, right? Okay, so let me bring up the lab, and we cut quite a bit of this lab out, guys, because they wanted you to wire all the flip-flops up to make the count. So I'm gonna bring up the actual lab so you can see how much we dropped off. That's up on pictures. That's it. And there's more, by the way. We got shift registers, we got one shots, we got a lot of stuff that we just don't have time to get to in this time. And this we're really struggling because we lost those 2 whole days, right? You understand? So that's why we're doing a lot of these. But we'll have time to do lab before the test. So these are the class lab we'll unless I see, we might do, Wednesday, we might do the exclusive ORs as a class, because that's a very important lab too. The exclusive gates. We might do that as a class, and then we'll bust it to turn y'all loose in your teams. You go back and finish up the inverting, the non-inverting, and all that other. So we've done a lot of labs, but I've recorded every one of them. So even if you were absent, you still have an opportunity to do it. So this is what they wanted us to do, guys. They want us to hook up this. This would be a modulus 8, right? And then they want us to do this one, which would have been a modulus 10 or a BCD counter. So notice they're resetting the dang thing on 9. And then they want us to hook up a 7447 just to see it, right? We're not going to hook up the 7447 because we know what it does, right? But we'll just look at the binary count on this, even on the last lab. But we'll
cycle back over at 9.
Or it's going to cycle at 10. It's a modulus 10, which means it's going to be able to count from 0 to 9. So we reset it on the 10.
How can we tell by looking at that?
I can follow this gate going back to the resets. Let me bring up my. So I've got it red. So I can follow these right here. And notice this would be, so this is my A, this is my B, this is my C, this is my D. Right? You understand? I follow this back. I'm resetting on this guy. And then I follow this other guy. You got to be careful. It's crossed over. And it's resetting on B. So we're going to reset on the 10. But we never see it because we reset on it, right? You understand that? It's not A. I'm not resetting on A. I'm resetting on D. So when this thing hits this, this goes to a 1. As soon as that goes to a 1, this guy's going to reset. So we're going to reset on a 10. So we'll never see 10.
Oh, it's truth table. Okay, because I'm looking at trying to figure out where, how can I, if I'm just looking at it, how can I just tell? But I have to go to the truth table to know that it's going to be.
A truth table for what? I know I'm going to reset on D. I know D is the most significant bit.
Yeah.
I know A is the second bit, right? So I come over here and that's a what? That's a 10, but we're never going to see a 10 because as soon as it tries to go to 10, it resets to what? 0. So I'm going to watch this thing count. It would start off here, and then it would go to here, and this guy don't draw as good as PowerPoint. 2, 3, and it's not as fast. 4. Now we're on the wrong side, right? So I'm not going to go through all. I'm not going to go through all these counts. No, because it's a bunch of JK flip-flops that has clears on it. And I've got them arranged as ripple counters. Okay. And what I'm doing is I know when I clear a counter, it will go back to what? 0. When I clear a JK flip-flop, it will go back to 0. The Q output goes to 0. Well, our Q outputs, that is the count. Right? You understand? Except they're bringing them down to 7447. So this would be A, this would be B, this would be C, and this would be D inputs down here. What do you mean? Because we're resetting on a 10. Because I'm bringing the date. This is a NAND gate. And the NAND gate says if it's a 2-input NAND gate, it says all inputs go high, the output will go low. Well, when this output right here goes low, what's it going to do to all my latches? It's going to reset. What happens when I reset? The output, the Q output goes to 0, but I'm outputting all of them. Okay, so what's going to cause both these inputs, of this NAND gate right here to go to a high? Well, when this Q output right here goes to a high, that's one high. When this Q output right here goes to a high, that's two highs. Now I've got all highs, what's going to happen? This right here is going to go to a low, and what's going to happen to all my Q outputs? They're going to go to a low. Okay. You follow that? Okay, so this is my A, this is my least significant, this is my B, this is my C, this is my D, that's my most significant. So over here on the right where we can see, I'm going to write these things down according to their weight, not according to their position. The problem we have with drawing counters is your inputs are always on the left and your outputs are always on the right. Now, when I do that with counters, it means my QA, my QB, CD are actually drawn backwards, right? You understand that? So over here, this would be A, this would be C, this would be A, B, C, D. Okay, so I start counting. Now, what I'm looking for is when this one goes to a 1 and this one right here goes to a 1, that gives 2 ones on the input of that NAND gate, and this sucker is going to reset, right? You understand? So would this reset it? Would a count of 0 reset it? Would a count of 1 reset it? Would a count of 2 reset it? Would a count of 3 reset it? Would a count of 4 reset it? Would a count of 5 reset it? Would a count of 6 reset it? Would a count of 7 reset it? Would a count of 8 reset it? Would a count of 9 reset it? Would a count of 10 reset it? So what did I count from? I counted from 0 to 9, which is a BCD count. But if I wanted to count, if I wanted it to count from 0 to 3, I would reset it on 4. Right? You understand? I just use a 1 inverter out there. As soon as this bit right here went to a 1, I would reset all my counts. So you reset it on the one after what you want to count to. So I can set the modulus of this thing anywhere I want to between 0 and 16. I mean, the modulus from 0 to 16, from 2 to 16. I would never have a modulus of 0, right? Of course, if I needed a modulus of 2, I would use I'd use one JK flip-flop. I wouldn't use a whole counter to get a modulus of 2 because one JK flip-flop gives me a modulus of 2, right? You understand, or divide by 2. But now I can get a divide by 2. I could get a divide by 3. I could get a divide by 5. I could get a divide by 6. I could get a divide by 7. If I wanted to divide by 8, then I would just use this one output right there, right? You understand that? I could get a divide by 10. I could get a divide by, if it's a 7493, I could get anywhere from a divide by 2 all the way up to a divide by 16, just by resetting it on whatever I wanted it to be. So if I wanted to divide by 3, I would reset it on what? 3. And I would take my output off of this guy right here. So you have to take your output off the last counter that's not, that you get a true output of.
Can you scroll that up?
Oops. Only thing I do is erase everything, guys. So part of your grade, guys, is we're not going to hook this circuit up. But what I want you to do is I want y'all to do the pin out. So this will be inside of one JK flip-flop. Remember, we got two of in a 7446. I'm sorry, 74 LS 476. We have two JK flip-flops inside each. So how many ICs would it take to hook up this circuit? Huh? So this right here would be one, right? This right here would be one. Okay, this right here would be one. This guy right here would be one. And that's a 7-segment display. It's not an integrated circuit. So whatever pin outs you use for this guy, then you need to do what? Do it on that one. And this is going to be a 74. The parts is on front, but this is going to be a 7400 or 74 LS100, and this is a 7447. So we're not going to connect this up because all we're doing is making a 74. All we're doing is making a 7490. So instead of me coming up here and wiring all that stuff up, right, you understand, I would just buy a 7490 and it's already wired for me. Or I would buy a 7493 and set it up as a modulus team. I know it's not because we're not going to wire it up. Okay, then y'all can't do that. I'm sorry. Thank you. Y'all need to say thank you.
I mean, because don't fit the 18-8.
Yeah, that's what we're doing. We're moving directly to the counters. Thank you. So we're not going to wire this one up. We're not going to wire this one up. What would be the modulus of this? By the way, even the lab is wrong. There's no way in the world I can reset this because this is too low actives. So what would be the modulus of this guy? The modulus would be 4. Well, no, we're resetting on 3, so the modulus would be 3. Whatever you reset on is the modulus of the counter. But it would only count 0 and 2. So this guy right here, let's see, so what are we resetting on? Let's make sure. No, that's not a 3, guys. It's not a 4, guys. It's not a 2, guys. I keep going back, but I need to just click on it. That's it right there. So here's A, here's B, here's C. Okay. So all we're doing is A, right? A, B, C. So this guy is hooked up to A. So we're looking for A to be a 1. This guy's hooked up for C. So it's a modulus of 5. Go ahead, divide. Did anybody say 5? I don't think so. Huh? Yeah, but the problem is this is not horseshoes, right? Not anymore. I fall. I tried to throw them. I got into playing washers. You guys play washers? People do it now with bean bags. You know, they set up what do they call it? Hacky sack or something. Well, we used to bury a can in the ground and play it with washers. Big washer. First time I played it years ago. It's the same game. And horseshoes, I was never really good. That cornhole. Huh? Huh? Bear the can, like I said, can. And you scored it the same way. So we jumped all the way here. So y'all did the pin out on 7493. So we saw it count. But what we're going to do here is we're going to see it actually divide. So this lab is we're going to take this thing. I'm going to put a clock input. What are we supposed to be running at? 200 kilohertz. I can't do that with this trainer. The best I can do is 10 kilohertz. So what would that give us? 10 kilohertz divided by 16. What would it give us on the output? So we should be able to do this. So we're not going to use a 10 kilohertz. We're going to use a 10. We're not going to use a 200 kilohertz. We're going to use a 10 kilohertz because that's the fastest that's available on the trainer. So we're going to see this thing divide. So I'm going to take this guy, look it up to my clock. Then I'm going to take my channel A. And then I'm going to hook it up. What's the clock pin? 1014, right? Okay, 14. And then what we're going to do is we're going to take the channel 2 input and we're going to move it around depending on which divide by we're going to look at. And we might have to change the speed, guys. We'll see.
Yeah, CP0 on the pole. We got CP1 on channel A.
No, well, CP0 is connected to the D output of the A output. So let's reword these the way the data sheet is. Or rename these. Because like I said, you won't see these on any data sheet that I've ever seen. So this is clock A. You gotta want to draw. And then I don't have anything connected right here. What I'm doing to make this thing work is I'm taking the QA output and I'm feeding this back around to the clock B input. This is not MR, this is reset 0. This will be 1. I'm sorry, this is reset 0. Yeah, 1, sorry. And then this is reset 0, 2, right? So this right here is going to give me a divide by 2. This This right here is this is divided by, I'm just gonna put the numbers up here, guys, because it don't, this will be a divide by 4. This will be a divide by 8. This should give me a divide by 16. I have these hooked up switches. I'm sorry, I didn't change those. Yeah, so this, yeah, so we can see these happen. They've got them both connected to ground. I have both of my switches down to a low. It don't make any difference. One could be high, one could be low, because it's a NAND circuit, right? So to reset it, I have to bring both of them. So I have this guy here hooked to switch 0, and I have this guy not to switch 0, to the output on the trainer, and then I have this hooked to switch 1 out. So y'all need to do the pin out, right? Because y'all gonna have to help me step through this. Some of y'all was not doing the pin out. Like I said, I'm doing the lab, so I'm grading heavy on doing the pin outs, right? You understand?
So you can see what we put by ground.
Yeah. And that's something, guys, you're gonna get into all the time. Them misusing the term ground. And that's done all through, it's common on every data sheet, they'll call that piece of ground that I do. But it don't have to be a ground, right? So it's something, and like I said, you calling it ground is okay, just as long as you understand what the difference between a common and a ground. But Brian will correct you over there if you call it
a ground. Yeah.
So here's the circuit. It's not much difference. All I've done is taken the input, and I'm gonna connect it up to a 10 kilohertz clock. I have it connected up to the clock output of the trainer now.
Okay.
Are we okay? Okay.
Yeah, I was just trying to see what top was.
Yeah, so we have to wrap that around on these counters on the 7490, the 7492, the 7493. We take the QA output and bring it back around to the clock B.
I was just looking at right.
QA, yeah. So what's wrong with my scope? We're not triggered. Okay. So we'll go over our trigger menu. Right now we're going to set it up the trigger on channel 1. So we just don't have the trigger up into it right now. And we're going to try to set it so we can see really good where these edges in. So this would be 1 cycle of the input clock. This would be 2 cycles. We're going to have to slow this thing down, guys, because when we get down to 620 kilohertz, we're going to have to slow the scope down some. But we'll identify where the cycles are, right? Everybody okay? Okay, so let's look at the QA output. Isn't that the first thing we're going to draw? And what pin is that? And we're going to have to trigger off channel 2. Oh, for some reason, I'll have to trigger off channel 1. This should freeze it. I'm not too crazy about this camera, but like I said. Should be. Let's see. Here's one cycle. We're triggered on the rising edge. Let me move this over so we can see the edge. So the rising edge here, 1, 2, 3, 4. I'm sorry, one cycle, 2 cycles. Over here, we're getting 1 cycle for 2 cycles. This is divided by 2. Still a 50% duty cycle because we're going on the power of 2, right? Okay, is everybody okay? Yes, no. See what y'all doing? All right. And then we're going to go to QB. Everybody ready? Everybody ready? Okay, so what's QB? What's wrong one, Rich? Sorry. One, two, three, 4. So for every 4, I'm just looking at the pulses. For every 4 of these, we have one of those. That's a divided by 4, right? Well, no, our output starts on high here. Well, if you, yeah, well, it depends on where you start yours at. So we can see 1 cycle. If you want to start it on low blend edge, it's still 1, 2, 3, 4, right? And it's still about. It's just that the scope is starting off on the rising. And on the next one, we're going to slow our scope down. So notice I don't know if y'all can see the actual frequency. It's 2.5 kilohertz. Of course, we don't have exactly 10. Well, let me try to get it as close to 10 as I can. Just don't have a really good fine adjust on it. That's about as close to 2.5 kilohertz as I can get. But if we check the input, it would be really, really close to 10 kilohertz now, right? Okay, guys, we're ready to move on. So the C output. Okay, so we're about to slow our scope down, right? You understand that? So we can see a whole cycle. But you're going to have to draw it relative to that. So So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 for one of these on the bottom. So 8 positive pulses, right? For one of them on the bottom. Now notice this guy actually we had to start from here because I don't see the entire positive because of where we're triggering at. Let me yeah. 1. I'm just counting positive pulses. There's the first one, right? 1, 2, 3, 4, 5, 6, 7, 8. So 8 cycles of my input gives me 1 cycle of this guy. So this is divided by 8. And the next we're going to slow our scope down. It's going to be a little harder to see, but because we're not doing 200 kilohertz, right? So this is 1.25. It should be divided by 8. What should be the next one? We ready? So what's QD? What's that? No, what pin is it? I'm
Oh,
sorry.
it's 10 might be better.
8, 9, 10. Yeah, so I'm gonna slow it down one. So here's one cycle. 1, 2. Let me get something where I can point to a little sharper. Well, we're starting counting on the low. It's just that where we're triggered from. So this is my trigger point right here. So this is where we should start counting from here. Let me get this on the line. So this is the first one. That'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then it changes. Yeah, so we're referencing from this point right here. Can y'all see the arrow up there? So what I'm doing is I'm looking at the first. Oh, I pulled it out. What pin? Yeah, so this is the first pulse right here. It's the high, right? Okay, you're right. So that would be, so this would be right here. So the first cut logo and edge. But what I was counting, I could count the low and the highs. It was just easy for me to count the highs. And they kind of blended together, but notice when I was counting, I counted up to 16, and it did what we counted. So if you start them on the same thing, it's okay. It's just that for here, how far does your upward? Don't they give you counts on the top? They give you 15 on the top. Yeah, but we won't quite get there because it's actually 16 pulse. You won't be able to. Yeah, the last one will stay low. You won't see it go back high because it's 16 pulses, so they didn't give us enough pulses. Always nice to be right.
Yeah, it is. But the problem is knowing how you was right.
So if I needed to divide by 16, then I could just take off on the D output, right? Now, of course, all the LEDs look like they're staying on all the time, are they? No, they're just flashing, and what's our eyes doing? LEDs are really, really fast. And that's why your pulsar probe, you know, not your pulse probe, your logic probe, if you ever look at a logic probe and it says high and low and both those lights are on, you know you're looking at a watch, you're looking at some type of clock. But you don't know the duty cycle. We can measure the duty cycle here. So what is the duty cycle? What is it? What is it? What is the duty cycle? It's the percent of the period that the waveform is high. You can't do duty cycle on this guy. My probe pulled out. So we've already done this, guys. So we're not going to hook up the 7447, but you got the pin out of that, right? Everybody okay there? Y'all can look that up. And you got the pin out of the 7-segment display. So every IC that we use in this lab So we got one called data sheets, right? That's at the very bottom. 7-segment common anode LED. And we have the common anode because we're using the 7447. It's a common anode driver. So there's common anode right here. So this is the one we have right there. Yeah. And here's the 7447, which is a 7-segment decoder driver, right? Here, this is right here. Okay? And the 7493, it's also up there.
So for the 7447, how would we put that?
So these are inputs. These are the outputs, right? Here's ground, here's power, and we're going to tie all these high. We're not going to be using ripple blanking. We're not going to be using ripple blanking on this thing. So we'll just tie these guys high, right? Lamp test, we're not going to use lamp test, so we'll just tie all three of these, sorry. We're going to tie all these three of these up plus 5 up. Make sense? Okay? So any pin that you're not using, you need to tie it to its inactive state, right? Understand that? So we're not using lamp tests. We're not using ripple blanking inputs or ripple blanking out. So we'll just ripple blanking in. So we'll just tie all these up to plus 5 volts. And the 7493, we've already looked at the 7493, which is right here, and I've listed it twice, even though they're both on the same data sheet, right? You understand that? Just so it don't get you confused. I could come up here and just rename that. So we're using the 7493. Oh, I've already got it out right here. So this is the 7490. We're not using that. This is the 7492. We're not using that. We're using the 7493. But remember, you got to take the what? You got to take the D output and connect it back into the clock B input for this thing to work. Yeah, the QD output and connect it back into the clock B input for it to work. So the modulus of a 7490 is 10. It's a BCD count. Of course, we have to take the what? We have to take the QH. So this is clock A. And I have to take this and put it into what? Clock B. So what would be my division ratio right here? I took my output right there. These are both 70. These are 74 93s. This is divided by 16 right here. So I'm taking a divide by 16, feeding it into a divide by 16. 256. So some of y'all said 32, but this would be like me taking 100 and divided by 10, right? You understand? Or taking 100 and divided by 2, and then taking 100 and divided by, no, that don't work out. So I'm taking 10K, let's say I'm taking 200K, and I'm dividing it by 16. Then I'm taking that and dividing it by 16 again. So let's put that in our calculator. So let's say 2K, first of all, let's say 2K divided by 32 and see what you come up with. And then take 200K divided by 16, and then take this answer and divide it by 16 again. You're not going to come up with the same answer. So every time you divide, they're multiplied, right? You understand? So this would be a divide by 256. So what would be my output frequency? This is 200K. 200K. 200K right, divided by 256, so it'd be 781.25 hertz.
Okay, I was going off what you had said.
Well, that's 200,000. 200,000.
You said about 32.
No, I said that was wrong.
Oh, okay.
I was trying to tell y'all because when I said if I failed to divide by 16 and divide by 16, somebody said that would be a divide by 32. And I was showing you that that's what. That's wrong. So if I take 200,000 and then I divide it by 16 and it equals, and then divide it by 16 again, we come up and get the same answer. So all you have to do, guys, so this guy would count from 0 to 255, right? But if I took the D output, here I would get a divide by, what would I get right here? What if I took my output right here? Well, now I'm taking a divide by 16, and I'm feeding that into a divide by 8. Because I'm taking it right there, right? So this is 2, 4, 8, 16. So now if I take it off the C output here, I would get a divide by 16 times a divide by 8. What would that give me? So I'd get a divide by 128. That makes sense. If I took it right there, I'd get a divide by 64, right? If I took it right here, I'd get a divide by 32. So it's just in powers of 2s, right? You understand? If I took it right here, I'd get a divide by 8, divide by 4, divide by 2, and that one, I'm sorry, divide by 2. Divide by 16, divide by 8, divide by 4, divide by 2. Everybody okay? Now the 7490 would be a little bit hard to figure out as far as your divide by. This guy right here would give us a divide by 2. But let's say I change this over to a 7490. There you go. So a 7490 counts from what? 0 to 9. So it's a divide by 10. So if this is a 7490 and I put 200 kilohertz in right here, what would I get over there? So what does the 74 give me? 7490 give me what? No, a 7490 is a divide by 10. So I'm taking a divide by 10, I'm feeding it into a divide by 10. So what would be my total division? Divide by 100, so what would I get out? Now this is not duty cycle. It wouldn't be a 50% duty cycle because it's not a multiple, it's not a power of 2. Huh? 2000? Oh. 2000? So if I took a divide by 10 and fed it into a divide by 6, what would I get? I wish I still had this circuit hooked up, guys. So if I fed a divide by 6, divide by 10 into a divide by 6, that would give me what? Just both of them together, guys. Give me a divide by 60. So if I had 60 cycles per second over here, and over here I would get I could feed that into some counters, and I could make a digital clock. So a lot of your digital clocks, this is all there is to it. They take Alabama Power, they convert it from analog over to digital with this little circuit right here. This is the same circuit that I had with and y'all did this in one of your first labs, right? So if we design this right, I could be bringing this in on this side, and over here I'd be getting this out. I could bring this into my counter. This would be at 60 hertz. I could divide by 60. Then I can bring that in regular BCD counters, and I can make a digital clock. Because that Alabama Power, that 60 hertz is very, very, very accurate. Everybody okay on this one? So 7490 gives me a divide by 10. If I take the D output and feed it into the next clock input, that's going to give me a divide by 10. 2 divide by 10s connected together gives me a divide by 100. Everybody understand this? Yes or no? And why? What comes up Wednesday? What do you think's on there? Should be audio. 4 of 3, right? Oops, not the data sheet. So we've already done this, so let's take this back. So I'm going to take it off my clock. And you know what the 7447 does. What does the 7447 do? It is a driver, but what type of driver is it? Of all the guys we talked about, what's the 7447? Yeah, it's a 770 display. It's a decoder. So decoder, and a bunch of y'all missed that on the questions about what the difference between an encoder and a decoder. And it says I need to take something and convert it from octal to binary. Octal, so we're going from another base to binary. That's an encoder, right? Y'all understand that? From binary to another base is a decoder, right? Or another code. So here we're taking binary BCD and we're converting it over to 7-segment display. So a lot of y'all missed that on one of the questions that y'all turned in. So y'all said, what would we use to convert an octal number into a binary number? Some of y'all said a 74138. That's binary to octal. That's not octal to binary. It's a decoder. Some of y'all said a 7447, which is a binary to 7-segment decoder. And the question was, what's required to convert a what? An octal number into a binary number. So that's not a decoder, that's an encoder, right? I don't remember. It's on one of the labs I just got through grading. 74138 is we're looking for a octal to binary decoder. A 74138 is a binary to octal decoder, right? You understand? We're looking for an encoder. We're not looking for a decoder. Right? Y'all understand? On one of the labs.
Oh, I remember baby.
I said a 74138 was a binary to octal decoder. The question said octal to binary. The question didn't say binary to octal. The question said octal to binary. Right? You know what I said. All right, you play that recording for me. Where I said we would use a 74138 for an octal to binary decoder. I'll give you credit. So we only looked at one decoder in that whole lab, and what decoder did we look at? Anybody remember? So all the lab was set up on. We only looked at one encoder on that lab. And what was the one encoder we looked at? So we didn't design the circuit, right? That would have been really hard. So this is a decoder. 74147. This is an encoder. To convert octal to binary, a 74138 is binary to octal. Some of y'all said 7440. Some of y'all said a 7447, which has nothing to do with octal, right? You understand that? So 74147 would do it. Huh? Yes or no? So this says what? Octal to binary. A 74138 takes binary to octal. Assume a 74 LS93 wired for a modulus 16 with input clock connected to clock 0. What would happen if QB were connected to CP1? Instead of the normal. So what would y'all think would happen?
It'll reset it'll reset instead of 1, that means reset QA, it'll reset QB.
Yeah, but QB can't change unless QA changes. I mean, that's a good point. So y'all hear what Brian said. So what we're doing is this is QA, this is QB, this is QC, this is QD. And then we have to take this guy right here and we have to feed it back into clock B. So for clock B to change, so QA feeds QB. So this is the way this thing is set up. Here comes my clock, and then I'm taking the Q here, right? And instead of taking it out, I'm taking it up here somewhere. And here's QB over here. It's coming right there. So QB, before it clocks, what I have to do is I have to take this guy right here, and this comes down here, right? You understand? I'm going to take this one, so this is pulse it, and I'm going to bring this around here and bring it into there. So when this guy right here pulses, this pulses. Okay, so here's my main clock right here. Here's clock A. Y'all follow this? But what I've done is I've really screwed up, is I've taken this right here, and I've done this. So what's going to be clocking B? We're just, y'all see nothing. So this thing, we would get the QA output would work with the QB. The QB, QC, and QD would not work. The counter would not walk. Wouldn't count. Yeah, it wouldn't ripple, right? That's a good point. Now visualizing, you hear what Brian said, it was obvious. It said, okay, we would count on B, but count B depends on QA, right? You understand that? What symptoms would be observed if your two resets were left floating? Don't know. We'd have to do it. Because the problem is that basic gates, the basic gates, a floating input is assumed to be a 1. When you get into these combinational logic gates, you don't know. So let's do it. And see if the thing actually resets. We'll see what it does. So what I'm going to do is let's make sure we have it set up to count right now. No, we don't. Okay. You'll see it over counting. Three, 4. So what have I done? That's okay. What I'm gonna do is I'm gonna reset it. Okay. Or let's put a count into it. I'm gonna float both my inputs. So this guy assumes it as a high. So what would happen? That won't count, right? Output stage it was 0. So this guy assumes it as a high. I don't know what I've disconnected, guys, but I've disconnected something. It resets on high. There's no inside the counters, which we're away from that, but from the output, it's just an AND gate. And like I said, somehow we've lost our count. But that's okay. We can see enough to do the rest of this troubleshooting thing. What would a modulus, what modulus would a 7493 count if the input is fed to Q0, QA is fed to Q1, QB is fed to, oh my goodness, okay, here we go. So y'all write this down so I can draw it on PowerPoint. This drawing application that comes with the recorder is just not too good. We're ready? Y'all got it? So this is reset. This is reset 0. This is reset 1. So we're going to take B to reset 1, and we're going to take C to reset 2. Oops, this is clock A. And we're bringing our count into here, right? And we're taking the QA output and we'll feed it into clock B. So what are we taking over to our reset? Okay, so QB is fed into one of the resets. And what's the other one? So here the QD output wouldn't even be used because we're never going to get that far, right? So what are we resetting on? Okay, but what number? So we'd be resetting on a what? So I start counting. What somebody said it? What? 6. We'd reset on 6. So this would be a modulus 6. We wouldn't take an output on D because D only gets when you get up to 8, right? So D would be going unused. C would be my highest output that I could take up to. So this is a modulus 6, so it would divide by what? It would divide by 5. Everybody okay? Yes, no? Yeah, the modulus would be 6. So the modulus is where you reset it on, right? You understand? And then your maximum count would always be 1 less than the modulus. So if I came over here and took it off the C output, then I would get a divide by 6. So this is basically right. And what's nice about the 7493 is it's got the AND gate in there, right? You understand? It's got the NAND gate in there, and you can usually set the modulus without adding anything else to it. Because I can monitor 2 inputs. If I wanted to monitor 3 inputs, then I could just use another AND gate. So this guy, we can set this thing up for almost any modulus we want. So if I wanted to divide by 3, then I would move these guys over here to the AB. If I wanted to divide by 4, then I would use that output right there. If I wanted to divide by 5, then I would hook it up between here and here. If I wanted to divide by 6, then I would hook it up from here to here. If I wanted to divide by 7, then I would have to use another AND gate outside, right? Understand that? If I wanted to divide by 8, I would use that output right there. If I wanted to divide by 9, I would reset on these 2 right here. If I wanted to divide by 10, then I would reset on these 2 guys right there, right? Divide by 11, right? 11, I need 3 inputs, but I would add another AND gate. Does that make sense? So I've got 2. What I could do, if I needed to divide on these things that need 3 inputs, then I would put another AND gate out here. And then I would bring this into one right there, and now I can monitor 3 inputs, which is the most you'll ever monitor, right? You understand that? So now I can get any division ratio out of a 7493 from 0 to 16. I'm sorry, from 2 to 16. I could wire it to do a divide by 2. I could divide by 2. If it's a 2, 4, 8, 16, I just use that outlet, right? So this guy right here is really, really neat. The 7490 it's just got the 7490 it's just got the AND gate built inside of it. So the 7490 is a divide by 10 if we don't change the modulus, right? You understand? The 7492, which we don't do any allowable, is a divide by 12. And why they do that, guys, I don't have any slightest idea. There's not even a base 12 that we would count in, right? You understand that? In a 7493. So what's the 2 categories of counters? BCD and binary. I'm going to bring up some more here. Right, so I think the rest of them you could do on your own, right? Let me look real quick. What is meant by ripple counter? It means that has to do what? Ripple through it. Show the wiring diagram of the 7493, so that's what we need to do. So let's look up a 7493. This guy is 74193, I'm sorry. This is really cool. So we're going to look at the data sheet. So 74192 is a BCD counter. 74193 is a binary counter. I've closed Blackboard out there. So. So we got 2 options on the test. Test 4, we can still give it on Wednesday, or we could move it to Monday. But if we move it from Monday, you're going to only have 1 day to study for the final exam. Remember, your previous test 2 is, your previous test 3 is before you take test 4, right? And then previous test 4 will be before you take the final. And guys, how many times can you take those? And what's the final going to be? It's going to be all 4 tests, right? Y'all understand that? So you've seen every question that's going to be on the final. You will see, you haven't seen, you will see every, and the final is all multiple choice. There's not going to be a part 1 on the final. Huh? About 300, I think. No, it's going to be a few, but it's not going to be 100. And I can lie with a straight face.
I see, because I was thinking like,
So 7493, guys, let's look at this guy. This is a really neat counter. I've seen these guys used a lot. 74193. It's probably on there. The data sheet might also cover a 192 because these things are so similar. Now this is nothing, it's a synchronous counter. So what the synchronous counters do is the count comes in and goes to all the clocks. And then they toggle it with the Q outputs. It's really, really neat. So they actually control the JK. So the advantage of a synchronous counter is it's got a lot shorter propagation delay. So here it is. It's in a 16-pin dip. But notice what it's got. It's at up down counter, which means we can cause this sucker to count up or count down. Now, how it does that, a down counter, we take the not cues and take it over. Instead of taking the cues, we take the not cues over. But we don't even need to know that. All we need to know is, okay, this guy can do what? Count up or count down. So if I'm going to send this to another counter, then what we need to do is tell it whether we're counting up or are we counting down. So look what this thing has. It has a what? It has a carry output and it has a borrow output. So if I was counting down and I had two of them together, then if I counted down, I would tell the other one to borrow. So what I would do is I would take the borrow of this one and hook it to the count down of the next one, and I would take the carry and hook it to the count up of the next. So now we got a 16-bit counter that either does what? Counts up or counts down. Also, we've got a data input. We've got an A, B, C, D inputs. And then I've got this one pin right here called what? Load. So what do you think we can do? We can bring a binary number into the A, B, C, D inputs and we can load whatever we want to this. So on this guy, we don't need to start counting from 0. So what I could do if I wanted to put 9 things in a box, I could load it with a 9, tell it to count down, and when it counts down to 9, it would generate a borrow, and I know my count is over. So this is a preloadable. We can load this with any number we want to. What do you mean? This is an input. So what I would do is I would bring the number I wanted to preload the counter with into my what? My A, my B, my C, and my D inputs, and I'd bring that sucker low. I would pulse it low, and whatever I brought in would be loaded into the counter. So I don't have to start counting this guy from 0. So we could set the modulus by loading it with a number, guys. I'm not going to explain that to it. So we could use, we could load it with a 5, and then we could clear it with a carry, and then it would automatically do the modulus for us, which is really neat. Anything else? Here's my clock input. So we'd pulse 1, we'd pulse this one. We'd leave this one high. We would pulse this one if we wanted to do what? Count up. We would pulse this one if we wanted to count down. So I've seen these guys use a lot. And a 7492 is the same animal, but it's a BCD count. What's that? Counts from 0 to 9. No, an encoder is something that takes a number in another base or a code and converts it into binary. So we would have an octal to binary encoder. We might have a BCD to binary encoder. So a decoder takes a binary number and converts it into another base or a code. Okay, y'all understand that? Yeah. So an encoder goes to binary, a decoder from binary. And I can understand why y'all swap those around, because you see octal in your head, you didn't see it said what? Yeah. To binary. So this is a 7493. So let's see what the question asks now. This guy is a really, so what is the question? Up counter. Oops. What did I do with it? So if we wanted it to count up, tell me what we would do. Is this the 190? No, this is the one, right? I know I got it up here somewhere. Okay, so what would we want to do if we wanted to count up? First of all, we would do the down key. We'll put the down pin to a high. And I got to draw that. Let me do it this way. So instead of trying to use this thing, which is so hard, I'm going to print the screen. Let's do it here. Let's do it. I've got it spread out so far. Here we go. So for what would be let me change my color so we can see this. My picture covered up where I come in here and change it. So we connect this to a what? High. We bring our clock in right here. Whatever we want to count, right? Or let's say count. We want to make this thing count to a what? Yeah. Make it count as BCD. So what would we do? Does it say a BCD counter? We could, but what we're going to do is we want to count from 0 to 9. And the 7493. Oh, there it is. Here it is. There it is. That's what I'm looking for. So here's the what? Clear. So what I would do is I would take, and we only got one clear, and it's what? It's high active, right? Y'all understand that? Yes or no? So what would I want to clear it on? I'd want to clear it on a 10, right? So what would I do? The B, right? And the what? And the D. Yeah. On an AND gate. It's got to be an AND gate because the clear is high active. Of course, y'all got to do a better drawing than this, right? So basically, this is the questions. I think I answered all the questions, so y'all shouldn't miss any of these, but maybe one of them, right? So counters are cool, but we didn't have time to get into shift registers. What do you think a shift register does? We can load it with a number, and every time we pulse it, it shifts it. Shift registers have been used for years to change parallel to serial. And then we would feed it into the input of the next one, and then we would shift it in. So basically, all your shift registers was to take us parallel to serial. We didn't get into one shots. We didn't get into timers. We didn't get into a lot of stuff that's out there. We just didn't have time, which is really, really neat. But the book covers a lot of other information that we just don't have any time to get into. Now, what advantage, and you're still going to run into counters, even though computers, we can write a program that counts. So we can write a program to count. So in PLC, we don't wire, in PLCs, we're not going to wire a counter. We're just going to put a symbol up there and we're going to say it is a counter. But it's done by software. So it might take, to program a counter, a 10-bit counter, which could count from 0 to 1024, it might take 100 lines of code to take care of everything that the programmer wants. Well, programs take time to run. Okay, y'all understand that? So that means none of your software counters could keep up with some of the counts that we have to keep up with today. So PLCs finally realized that. So when PLCs first came out, the only counters you had, guys, were software counters. And then we got to these encoders, these guys that we use to set the speed of a motor. And them suckers are putting out thousands of pulses per second. And those software counters couldn't do what? Couldn't keep up with it. So what did the PLC have to do? Well, this went back, we call them high-speed counters, and those are basically hardware. Those are built into the PLC. So they had to go back to hardware counters because the software counters couldn't do what? Keep up with it. So the advantage, so you're still going to run into discrete digital circuits, even though we're moving all into a lot of programming, because programming software is slow compared to hardware. So the advantage of hardware over software is it's what? It can be a lot faster. Huh? No, it's still digital. So we're talking now is just digital. So in PLCs, didn't you take PLC, somebody else, and when you program a counter, you just put a little old block up there. Well, the problem is that's done by a program. In a program, you have an instruction. So if we looked at inside the 1100, it tells us the amount of time it takes for every instruction. So we might look at a counter and it might say 20 milliseconds. So if you try to give it a pulse past 20 milliseconds, it's going to just give you the wrong count. So what we do now, I don't know if you ever seen some of these things, some of these can manufacturers and stuff where these cans are flying past those things and they look like a blur. A PLC couldn't keep up with that. Why? Because it was all software. So what they've done is they've gone back to what? Hardware. You can still use the software counters, but anytime you get into something that's extremely high speed, you have to move into the hardware counter. And hardware counters are not programmed. What your program does is access the count. So you say, okay, what's in the count? And so they've had to do that. So guys, that's it. So what we're going to do on test 4, I'm going to put it up there now, right? You understand that? And then test 4, what we're going to do is we're going to take the test at the start of class. And I don't know where Brian's at, and I don't know where Jackson's at. But we're going to take the test at the first of class, and then we'll be in lab after that. And then Monday we'll be in lab all day. And give y'all a chance to do what? Catch up with what we haven't done as a team, as a class lab. So we should have time to get through with all the labs because most of y'all are already up on I think low active logic. If y'all can remember where y'all was at. But we had a lab due today. And like I said, if you wasn't here for last Wednesday's class, what did I do? I showed y'all how to get that, right? Okay. I was here, I showed y'all where to start, where y'all could finish it up. Well, there's my alarm telling me it's time for that. head out.
Right on.
I got to run over to another class, and I'll come back and look at the lectures and multi-lectures. So that's the lab, guys. I had to split three different lectures because I kept having to stop the lecture so I could use my computer to do that. So I split three different lectures, lowered it down, and stuff. I got to run over to another class.